Hello, I'm Awaz Gautam from Green Group, and we were given the topic aquifers and groundwater level. Uh, and the topic was pretty open. Whatever information we can come up with to make relational database, and then graphical maps or arc maps that we can plot. So we were given the study area of Southeast Texas, and to move forward with our project, I'll start by the objectives of our project. One of the main objective of our project is to create relational database, and then store the table whatever we come across while doing our task of plotting the graphical representative maps. Actually, we have a single map that is a graphical plot of average water level of major wells in each county, and pretty much tables that we come across that we plotted while doing the objective. And the sub objective, and I would like to mention, is to use Python, GIS, database tools, and whatnot while writing the program. The area of study is simply the map. The source of data that we used is for the groundwater data. We got data from Texas Water Development Board, and it was groundwater. Here's the link to that. And the other data we used was GAM file data. For this, and we use groundwater data and GAM file data to create relational database. We performed our objective by using these two, and for the plot of map we use county map of Texas that was acquired from TextDot, and the GAM files, and the groundwater data file. And these are the tables that we have in our relational database: grid detail, grid info, layer depth, layer info, well cell, well main, X and Y. X and Y are the table that are formed by joining. We joined, or we showed the relation between the tables in two different ways. One is by assigning a primary key and secondary key by creating the table itself, and the other way was to write a command to join the tables. And save them in the form of tables. So these are the XY table. And in this slide, I would like to show the common feature that we have, that we used for our relational database, was cell ID that was unique in one of the table, and that was being repeated in the other table as primary key, foreign key. And similarly, we had the layer names and description that was unique in one table as primary key, and was repeated as foreign key in another table. And we also did spatial join. We also have a spatial relationship between two different tables, since we have the data from grid GAM files and the groundwater files. We related them by spatial feature, by the location where they actually occur. So that was our other relational database part. And this is this lies towards the conclusion of our whatever we showed for the visualization. That is the average water elevation calculated by using major wells table from groundwater database, and these are the location of wells. For doing this, we actually combined well main table. We got the location from well main table, and then we got the depth from major well table, and which was clipped by the county map of Texas, Southeast Texas, to get the average water elevation in each county. The graph, I would like to talk a little bit about the graph. Some of the values in the graph says negative. The positive these are the depth from the surface of earth, like at which the water level is present, and the negative value means above the surface, like it's slightly higher, but it could be because we could not take care of some junk data over there. But this simply means that the water uh, well was under the pressure flow, and the water was flowing above the ground. And since we have a big database, like we got every kind of data we needed, and beyond that, we whatever data we had data enough, like more than what we could handle. So there's always potential, like we just deal with water level, we could go to water quality, we could come up with water lithology, soil characteristic thing. We can do pretty much, and then do something for the future works. And this is our presentation. Further, my group mates will show what we did in code.
Hello, I'm Sanjay Paul, and I'm from the green team. One of our group mate, Aj Gautam, has described the presentation slide, and now I'm going to describe the code. In this, at first we import the libraries, NumPy libraries, and for warning, the warning SMS, we import warnings files so that we can ignore it, and then we import the HGM file, DIS file, because our file format was in a in a number, and here we can see that we import the file as a for creating a matrix form. Then then we reshape this file into in 5 layers, and here we have 137 rows and 250 columns. Then we separating this separating this file of its depth, and of for the 4 aquifers, and then creating a database. And here we can see that we import the pandas library to create the data frame, and after that we use using a for loop to create a table, and here we using a law, and after that we save this into a CSV file, and then we create another table, and as its depth layer. That's it. Then after that we create a manual table, which is regarding to checkout, even line top and break line top, Jasper top, Jasper bottom, and then we save it as a CSV file, and we in this point we imported the raw data, and for our computer clean up the memory of our computer, so that we can work easily. Then we import this table over here, and we use the GeoPandas library to import the shape files. Here we can see that and we use two tables. One is the state wellman tables, and the another is the measure level table. um, and this is the uh, well-main table, and converted it's in a CSV file. And then here we actually convert this file, this longitude and latitude in the global version, because for the our special join, the and the global SR ID is 4269. After that, uh, um, yeah, here we can see that this and we use a geometry point, because map, if we have to create a map, we have to go through the geometry. That's why we create a geometry point. And then we special join Wellman and the grid table. From this and connect into a inner join. From this, one of my another groupmate will describe the rest of this. So
Yes, sir. Good afternoon. We are assigning as a green team, and we are working on a project that were given by our head and chair department, Dr. Venkatesh Udamari, and we are given an objective of to find aquifer related data and water level elevation for all different 14 counties of Southeast Texas. So my friend discussed about how he grabbed a state well number and cell ID. So now I am going to discuss about creating a relational database. First, we imported OS library and SQLite 3 libraries to working on it. So we created empty database with cell ID as primary key and copying data from existing table. We got the already existing table over there. So we need to create an empty database with a cell ID as a primary key so that we can assign to the other tables, or we can join them spatially. So there's we written the code in a line 58 and 59, and then we ran a query that execute about select depth of and layer depth of inner joid from grid info table. So and then we used GeoPandas platform to import shapefiles of grid. That's the only library that supports for the import shapefiles for a grid. So we use that. Then we imported well-main table from groundwater database, which we downloaded from TWDB, Texas Water Development Board. So we ran the file and we created geometry column, and then we gave the name well-main of that data, well-main that database, and it comes with the centroid, cell ID, county names, such different types of columns. Also, it contains a geometry. So we need to convert longitude and longitudes to geometry, because it is very easy to understand for Python to read the geometry points so that it can be executed on a map. So what we did, we grabbed the state well number. Now we need to add more table to the database, because we do not have sufficient data available over there, so we need to what data we need exactly. For that we need to add more tables to the database. So and then we are going to joining tables by values. So well cell and well main, that two tables could be joined with the inner join command that we used here. And then we imported grid shapefile that we got from geodatabase package in our GAM files. We imported that to QGIS, converted to ESRI shapefile, so that we can come to know about that what exactly the point at which aquifer and wells are located is, and we can easily come to know about like how to join between grid ID and cell ID and well ID. So it's just a plot that describes about like a grid, like how grid we can see this is the grid. And now the full and final portion of the code, like it's a visualization. We need to implement like for Southeast Texas, especially for a county of Southeast Texas, the NAD 83 system, CRS EPSG 4269, that's the keyword that comes with the Southeast Texas counties, especially for. So we run a file to the Python, the Southeast access.shape file, and then we made a V inner table that comes with the state well number, county, aquifer code, aquifer, latitude, longitude, well depth, and all different kinds of data. And then we need to take an average depth of water of different wells according to their state well number, and we also provided a latitude and longitudes over there and a well depth. So it comes for the all different 14 counties of the Southeast Texas. And now we need to plot the data on a map as a bar graph. So we used matplot library or pyplot chart. So we plotted bar graph of land use in ratio to planted area. So for all different counties, this graph shows the water level, the positive values of the water level from the datum surface. It shows that water level, it's just below the ground surface, and the map showing two negative values for the water level depth. It shows that water level is above the ground level surface. So yeah, that's all, sir. Thank you.